We are in discussion for calculating gradient normal vector and gradient surface vector. Okay, so for single dimension, we have already calculated a gradient normal vector and gradient surface vector. So if this is x-axis and this is y-axis, this is independent variable and this is dependent variable. And if this is the equation of a line, that is y equal to x square, then at any point on the line, we can calculate the differentiation. We can calculate the derivative. If we calculate dy by dx at any point a, x equal to a, then if y equal to x square, then dy by dx is equal to 4x cube. If that is true, then what is differentiation? Differentiation is if there is a unit change across independent variable, then how many unit of change we see on the dependent variable. So rate of change. So if that is true, then if I get rate of change of a particular line equation at any point, then I can have another equation of a straight line. So that is what we are talking. So if this is x-axis and this is the line y equal to x square, then any point on the line, if I calculate dy by dx, then whatever we can, so at that point, what is change in y that is seen per unit change in x. So rate of change in y that we see. If we know the rate of change in y, then if I have an equation of a line y equal to mx, where m is the rate of change dy by dx, then if this is x-axis, this is the line, at this point I am talking, then new line will be tangent. This is what we have seen. So equation of the tangent line is y equal to mx. If it is passing through origin. If it is not passing through origin, then y minus y0 equal to mx minus x0, where it is passing through a point that is x0, y0. Okay. Now, suppose that we are talking where a kind of uh, uh, x equal to a. What about x equal to a? If x equal to a, then y equal to 4aq(x). That is the equation of the line. If x equal to 1, then y equal to 4x. Okay, so equation of the line when x is 1 is y equal to 4x. Now, this is the equation of the tangent line. If I want the equation of a vector along the tangent line, so vector has no intersection, it will pass through one. This vector has only direction and magnitude. So equation of a line is y equal to mx, then the equation of the vector would be y vary 4 times to the x. So I plus 4i, I plus 4j. That is the equation of the tangent. This is what we saw. So equation of the tangent is I plus 4j. This is one thing. Now, if y equal to mx, then it can be represented as gradient vector. This is what we have seen in the past. So you can refer to those videos, gradient vector. So if y equal to mx, then y equal to m is dy by dx. Nothing but variation of y, partial derivative of y along x-axis. If that is true, then we have y equal to fxx x. Now, so where the fxx is called gradient vectors x component. Suppose that y equal to x to the power 4 is the equation of a line. Now, we can make it as a kind of a third dependent variable, two independent, like y I can take that side. So x to the power 4 minus y equal to 0. This can be like a general equation of a line with two independent variables. If that is the case, then variation along x-axis is 4x cube, whereas variation along y-axis is minus 1. Okay, if I consider third variable as z, then dz by dx is 4x cube and dz by dy is minus 1. Okay, if that is true, Then we have a gradient vector whose kind of x component is 4x cube and y component is minus 1. If that is true, then if x is 1, that will come as 4I minus j. Okay, so 4I minus j. So if that is true, then gradient vector is 4I minus j, whereas tangential vector is I plus 4j. If we do dot product of these two, it will come as 0. So if there is a if there is x-axis and there is a line equation y equal to x square at any point, the tangent is at any point if I calculate the derivative, whatever derivative comes, and I put the derivative as m, then y equal to mx is a line equation of a straight line. And at that point, the straight line is tangent at that moment. If that is the tangent, then we saw that the tangential vector or gradient line vector, equation of that, and gradient vector or gradient normal vector. If this is the gradient vector, then gradient normal vector is perpendicular to this vector. Okay, so gradient vector is this, then tangential surface vector is this. They are perpendicular to each other. If that is true, then we saw that this is how if we know the gradient vector, then we can think as tangential surface, not a line vector or gradient line vector be orthogonal to it. Now, same thing what we have seen in 2D. So now we will see in 3D. So we have a paraboloid. We have a kind of paraboloid. Okay. So this is origin, and this is how paraboloid along x-axis it is varying, and same it is varying along y-axis. So this is paraboloid. Okay. This is a sphere. So equation of the paraboloid is fxy, because it is a 3D, so fxy equal to x square plus y square. When x and y is 0, when x and y is 0, this is the origin. Whereas if x grows, then it will grow in kind of polynomial fashion, square. If y grows, it will be polynomial function as a square. Now, how we can calculate what is the analogy of the gradient vector and what is the analogy of tangential surface vector? So that comes in question. Now, if we have uh, if we have now fxy equal to x square plus y square, that is the equation of a paraboloid. Okay. Now, first idea is that we should calculate the tangential surface. Now, if this is the paraboloid, then at any point, so this is xy plane. This is x-axis. This is y-axis. If this is x-axis, this is y-axis. Then vertical is z-axis. X-axis, y-axis. Then vertical is z-axis. If that is the case, then any point on xy plane, will map to a point in z-axis, that is fxy, function over x and y. Okay, so suppose there is a point on x-axis somewhere, it leads to a z here. Okay, there is a point on xy plane that leads to z here. Okay, so many z if we add from the xy plane, then it constitutes a paraboloid. Now at any point, if we, like, if x is something and y is something, it comes here. Okay, the z comes here. Then what is the variation of z seen along x-axis? What is the variation of z seen along y-axis? So these two variation we have to calculate. In single dimension, we calculated variation of y along x-axis one, because it was a 2D. Now it is 3D. So variation of z, the variation in vertical direction along x-axis, vertical of variation in vertical direction along y-axis. These two axes we have to calculate the partial derivative. That is the kind of concept. Okay, so we have to calculate. Okay, so we have to calculate the partial derivative along. Now, if at any point, if I calculate partial derivative along x-axis, partial derivative along y-axis, then we are calculating rate of change in x along rate of change in z along x-axis, rate of change of z along y-axis separately. This is what we are doing. Suppose rate of change along x-axis is like this at that point. So every point tangent is different because dy by dx at every point is different. Like we say y equal to 4x, y equal to x to the power 4. Then dy by dx is 4x cube. If x is 1, then it is 4. If x is 2, then it is 8 into 4, 32. If x is 3, then it is 81, 4x 9, 27, 27 into 4. So that much. So dy by dx, the rate of change is growing with the x. So it's a function of x. Now, if we want in 2D also the partial derivation along x-axis, partial derivation along y-axis, how much z is varying along x-axis and how much z is varying along y-axis. So if we calculate, suppose z is varying along x-axis at that point, is like this, and z is varying along y-axis is like this. Okay, suppose. So y-axis, if we grow in y-axis, z is growing, but if we grow in x-axis, z is decreasing. If that is the case, now we have both the calculation dz by dx and dz by dy. If we have two calculations, then we can think of a surface where z equal to m1x plus m2y, or z minus z0 equal to m1x minus x0 plus plus m2 y minus y0. Z minus z0 equal to m1 x minus x0 plus m2 y minus y0, where x0, y0, z0 are kind of intersection on their axes if others are 0, or it passes through a line x0, y0, z. Okay. Now, if we think that it passes through origin, or we don't take care of it, only the kind of axis, then z equal to m1x plus m2y. So m1 is dz by dx and m2 is dz by dy. So if dz by dx is like this and dz by dy is like this, what kind of surface I expect with the equation, these equation z equal to dz by dx x plus dz by dy y. So if so on along x-axis is it like this, and along y-axis it is like this. So this is the surface. Or if along x-axis it is growing and y-axis it is coming down, it is like this. If it is growing in both directions, then if along x-axis it is growing and along y-axis it is decreasing, it is increasing, sorry. So along x-axis it is increasing, along y-axis it is decreasing. So it is something like this. Okay, along x-axis it is increasing, along y-axis it is decreasing. So z equal to m1x plus m2y. In single dimension, we had y equal to mx. We remember well. Y equal to mx. Now in 2D, z equal to m1x plus m2y. So if I know this equation, then at any point we can have now the tangent. So at this point, the tangent is like this. At this point, tangent is like this. At this origin tangent is like this. Here, tangent is like this. So everywhere, the m1 dz by dx or dz by dy would be in function of x and y. So varying upon the x and y, we will have different dz by dx and dz by dy. So considering the paraboloid where fxy equal to x square plus y square, if that is the case, then okay. Now if I take if that is the case, then dz by dx is 2x and dz by dy is 2y. 2x plus 2y. So z equal to 2. So if point is A and B, then z is equal to 2ax plus 2by. So that is the equation of tangential surface. Now question comes first is, what is the gradient vector? So gradient vector z equal to x square plus y square. If you know that, if we bring it as an equation, then it will come as x square plus y square minus z equal to 0. If that is the case, then gradient vector would be with the partial derivative 2x, 2y and minus 1. So 2 at any point a b, it will be 2ai plus 2bj minus k is the equation of gradient vector. Okay. So the equation of tangential surface is x square plus y square minus z equal to 0, or z equal to x square plus y square. I'm sorry. So this is the equation of graph. Okay. So if we talk about the tangential surface, then z equal to 2ax plus 2by. This is what we calculated. Z equal to m1x plus m2y. m1 is dz by dx and m2 is dz by dy. So z equal to m1x plus m2y. This is the equation of the gradient or tangential surface. Whereas the kind of, if we talk in gradient vector, then it is, now it is 2xi plus 2yj minus 1. So x square plus y square equal to z. That is the equation of the graph. So x square plus y square minus z equal to 0. Then gradient vector is 2x I plus 2yj minus k equal to minus k. That is the gradient vector. Or at any point AB, 2ai plus 2bj minus k. That is the gradient vector. Tangential surface z equal to m1x plus m2y. So dz by dx is m1, then it is 2a, and dz by dy is m2, then it is 2b at any point a and b. So z equal to 2ax plus 2by. 2ax plus 2by. This is tangential surface. Now the question arising is, if this is the tangential, if I know that, if this is the tangential surface, okay, so so if this is the paraboloid, then this is the tangential surface. If this is the tangential surface, I know the tangential surface equation now. If this is the tangential surface, so I know the equation of the gradient vector, because I know it is perpendicular to tangential surface. So gradient vector will be only one. Can we see? Vector never think about interception on x-axis, y. It's only direction. Okay. So a vector that is perpendicular to the tangential surface is a single vector that we have calculated as gradient vector. Now this can be said as normal to the tangential surface. What is the equation of the vector on tangential surface? That is the question. But this vector can go in any direction on this surface. That is the problem. This is not single 2D, it's 3D. So in 3D, if I have a surface, then I can have so many vectors on the surface, and all the vector would be normal to gradient vector. Okay, so that is the problem. So all the vector on this surface would be normal to the gradient vector. Then what is the actual tangential vector we are talking about? Okay, so we are talking about a vector. If this is the gradient vector, then it has, this vector has three components, x, y and z. Can we keep x, y constant? Whatever x, y this guy has, same x, y, only z will vary. If we vary only z, then it will be exact what we are looking. if this is perpendicular to the tangential surface and keeping x, y, suppose it is like this. This is x, this is y, x and y. If this is the tangential vector, if this is the gradient vector, then it has x component, y component, and this is the, suppose this is the gradient vector. Okay, this is the tangential surface. So it has x component, y component, and z. Can we see the z how much it is? Now, keeping x and y constant, can we vary z in a way that it will come to tangential surface? If it comes to tangential surface, whatever vector it is showing, that is a tangential vector. And this vector would move in a direction where it see maximum change in the graph. That is a pioneer. So if suppose if this is a tangential vector and I vary only z, not x, y component, then it will come to a vector that is perpendicular to the surface. Okay, so what is gradient vector? Gradient vector, we have a calculation as z equal to x square plus y square, or x square plus y square minus z equal to 0. So 2x, 2y and minus 1. So at any point a b, 2ai, I is the unit vector along x-axis, 2bj, j is unit vector along y-axis, and minus k. So, okay, so k is the z-axis. So 2ai plus 2bj minus k is the equation of gradient normal vector. If that is true, then what is the equation of gradient surface vector? Keeping x and y constant, then it will come as 2ai plus 2bj plus something alpha k. That alpha we don't know. But these two are normal. So a plus a 2ai plus 2bj minus k dot 2ai plus 2bj plus alpha k equal to 0. Then 2a square, 2b square minus minus alpha equal to 0. Now you can calculate the alpha and you get the tangential surface vector. But can we see the tangential vector surface? We calculate tangential surface vector. What we are calculating from the gradient vector is 2ai plus 2bj plus alpha k. So x and y component is same as the gradient vector. Same as what we started with the equation of tangential surface is nothing but z equal to m1x plus m2y. Same thing. So z equal to m1x m2y. So m1 and m2 in the tangential surface vector is same. So m1 is taken from gradient vector. So x component, this is m1 actually gradient vectors x component. M2 we have taken gradient vectors actually it is M2 is gradient vectors y component. Only the z parameters coefficient is different. So how we can calculate the tangential surface vector? First, how we calculate the gradient vector? So whatever the equation we have, like z equal to x square plus y square, we make in one equation. So x square plus y square minus z equal to 0. Then we calculate all three components of gradient vector. So 2ai plus 2bj minus k. This is the equation of gradient vector or gradient normal vector. Now, if we have like this, then tangential surface vector equation would be normal to it. And we want only the z component to change. If that is the case, then 2ai plus 2bj plus alpha k is the equation of the tangential or gradient surface vector. Now, if we make dot product of these two, then we can get the value of alpha and we get exactly, okay. Now, if this is the paraboloid, then at any point, if this is the tangent, at any point, if this is the tangential surface, okay, if this is a tangential surface, then exact perpendicular to it is the gradient vector. Okay, if that is the case, then tangential surface vector is perpendicular to this. Okay, keeping x, y constant. So it is like this. Now can we see this? It is exactly, it is passing the highest possible slope where the kind of function would change. Okay, so this is the story of calculating kind of the gradient vector, and gradient surface vector or tangential surface vector. Okay, so it is too hot. Lahub Wahed Har. Okay, so Wahed Har or Lahub, it is too hot. So I see that I can get something. Okay, so to beat the heat, I have now kind of it is a sugar cane. Okay, so it's not bad. It's really very sweet, and it's not a tangential surface. Nice one. Mm. Sweeter to sugar, that white poison, what we eat, sweeter to jaggery. It is the best sweet thing that you can have. Enjoy it.